Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu, and today we're going to talk about Bohr's model and atomic spectra. Okay, right to the topic. What is the Bohr's model of hydrogen atom? There are a few postulates of Bohr's model. So first, the hydrogen atom has only certain energy levels, or use a fancy word, stationary states. Each level is associated with a fixed circular orbital of the electron around the nucleus. The higher energy level, the further away is the orbital from the nucleus. So in other words, you can imagine the Bohr's model to describe a hydrogen atom as an onion. In the center, there's a nucleus. So outside, we have different rings. Each ring is an electron orbital, and electrons are in each electron orbitals. And each orbitals corresponding to an energy level. Okay, the second, atom doesn't radiate energy in the same stationary state. In other words, if electrons stay in one ring of the onion, this onion does not change. It does not shine lights, does not absorb or emit lights. It's very stable. It will be as it is. Third, a photon is emitted or absorbed when electrons jumps between energy levels. Now here's where the change can be. If we have electrons in one circle of the onion ring, and that electrons jumped to different rings, then that causes an energy difference of this atom, and that energy difference corresponding to the absorbed energy. Well, you need some energy to kick the electrons from lower level energy to a high level energy, or the atom will give away energies as in the forms of light. So when electrons jump from outside energy levels to inside energy levels, the atom will emit electrons. Okay, so here are the postulates of Bohr's model. If we want to give you a better schematic of how these Bohr's model of hydrogen looks like, beside this onion ring, you can imagine this energy levels as steps. Okay, there's nothing in between. The electrons can only jump in between different energy levels, different steps. And each step does not have the same height. Okay, the closer to the nucleus, the higher difference between neighboring steps. Okay, so some key features of Bohr's model. First, principal quantum number, n, or integer, it's just an integer, and electron orbit. So there is a Princeton quantum number n that corresponding to which energy level you are in. N equals to 1, 2, 3, 4, 5, to as many numbers as you want. And further, larger the principal quantum number, the further away the energy orbital, further away the electron orbital to the nucleus. Okay, and that's really only related to the electron orbit. Okay, and we have a ground state. Well, when you say state here, it's again a fancy way to say which one has a smaller energy, which one has a higher energy of the whole atom, which one is most stable one, or which one is not that stable one. The ground state, which means n equals to 1, the energy level equals to 1, is the most stable energy, the smallest energy you have. Well, the excited state, when you get excited, you have more energy, right? So when the energy n is larger than 1, which means 2, 3, 4, 5, 6, 7, 8, well, and other numbers, etc. Those levels, those energy levels are refers to an excited state. Or if an atom has electrons in this jumping from a lower energy level to a higher energy level, we also can call it in the excited state. Third, the absorption and emission of light, that actually gives us the atomic spectrum. We have the atomic absorption spectrum as one of the analytical methods to identify what atoms, what elements are there in your samples. So that's based on this principle. When the atom is excited or it absorbs some energy, it does not emit or absorbs any kind of energy. It can only give you the energy that matches the energy difference between any of the two energy levels. So if you see like all the possible energies an atom can emit, then each energy have its own fingerprint of the energy levels or the wavelengths, corresponding wavelengths or frequency of the light it can emit, right? And that gives you the atomic spectrum. Okay, and we can also use Bohr's model to explain the atomic spectrum very well. However, there are some limitations of Bohr's model. First, it only works for one electron system. For example, hydrogen has one electron, helium plus originally had 2 electrons, and because of its 1 plus, the helium 1 plus has only 1 electron, or lithium 2 plus, the barium 3 plus. So it only works for one electron system. If we have multi-electrons, more than 1 electrons in the atom, and then there are other things saying electron-electron repulsions and additional nuclear electron attractions, and both of them are ignored in Bohr's model. So in Bohr's model, we don't consider electron-electron repulsion. Both electrons carry negative charge, and when the two negative charge get close to each other, there is a repulsion between them. Because now we only work with 1 electron, so we don't need to consider that. And also, if we have multiple electrons, now the nuclei electron attraction, the positive and negative attraction, should be kind of split between the 2 electrons. So we have additional nuclear electron attractions when you have multi-electron system, and that is not considered here in Bohr's model either. So bear these 2 limitations of Bohr's model. If we we only work on the hydrogen atom, then Bohr's model is perfect. Okay, so I want to talk a little bit more about the atomic spectra, especially the line spectra of the hydrogen atom. We focus a lot on hydrogen atom. It's the easiest atom to describe in the quantum theory. Okay, so each of this electron orbital or energy level corresponding to a line here on the right. So you can see on top, so the energy increases from bottom to top, okay? They have different criteria in defining energy. So they say for an atom, the farthest away, the infinite distance has an energy of 0, okay? And that is larger than all the energies inside of the atom. So all the energy levels here has a negative value. Okay, energy is the absolute energy sometimes does not matter that much. The difference of the energy matters most. Okay, so when you write these energy levels, if you remember the stairs we showed before, the closer the energy to the nucleus, the larger the gap is. Okay, so it starts from the 1. You can see 1 and 2 has a larger gap. 2 and 3 has a smaller gap, and then 3 and 4 has even smaller gap. So approximately, you can see energy level 2 is in half between energy level 1 and infinity. Energy level 3 is kind of in half between energy level 2 and infinity. So that gives you an idea what's the difference between them. Well, okay, so when electrons jumping between these energies, we know they can emit atomic spectrum. We also can call that line spectra. And there are different categories of line spectrum because of this energy difference between the energy levels. If we have electrons jumping from higher energy level, does not matter whether it's energy level 4, 5, 6, or 7, or etc. As long as it jumps from the higher energy level to the energy level of 3, it will emit infrared series. It will give you infrared light. or only when you provide hydrogen electron with infrared, it can ignite the hydrogen energy level from 3 to higher energies. Okay, so infrared series can also be named Paston series. So you need to remember the name with both Paston series and infrared series, and they are the same. Okay, so if we have a higher level of energy that jumps to energy level that equals to 2, okay, this one, the second one, 2, then we have visible series. That means it emits energy in the region of visible light. Also, it has another nickname, Bohr series. If we have higher energy level, electron in the higher energy levels jump to the energy level of 1, then we emit UV light series, UV ultraviolet lights. It has another name, Lyman series. So in the question, in the exam, you may given information of energy jumping between different energy levels and ask you to define which line spectra that belongs to. So you need to know, you need to focus on the ending levels or the smaller levels. If the level equals to ending level is 1, then it's UV light. Energy level is 2 is visible light or Bohr light. Energy level equals to 3, then it's IR light or the Paston light, Paston series. So 1 to 3, UV light, visible light, IR light. And another way to understand that is UV light has the smallest frequencies and the largest frequencies and the highest energy. So when you jump from higher level to level 1, because of the big difference between 1 and 2 energy levels, you have the strongest strongest light you can emit. So the UV light, the strongest of the 3, corresponding to the ending level of that n equals to 1. Okay, so another way to remember these nicknames, remember there are only 3 different nicknames here. So the longer the wavelengths, the infrared has longer wavelengths than visible light than the ultraviolet light. So the longer the wavelengths, the longer the name of this series. So Paston has more letters than Bohr, which has more letters than Lyman. Okay, so if you can correspond in that would still work. Okay, so we mentioned a little bit about energy levels. Besides knowing the series of the light a hydrogen atom can emit, we can actually accurately identify and calculate exactly the wavelengths or the energy a hydrogen atom can emit. So let's talk about equations about energy levels of a hydrogen atom. For Bohr's model, energy of a hydrogen atom, or energy of any one electron system equals to negative 2.18 times 10 to the negative 18 joule, and then z squared over n squared. That z is the charge of nucleus, and n is a principal quantum number that corresponding to the energy level. For hydrogen, it only has 1 proton in the nucleus, so the charge of nucleus is 1. We can simplify this equation to E equals to negative 2.18 times 10 to the negative 18 joule 1 over n squared. This equation is very important. It defines any energy level in a hydrogen atom. Okay, and for each atom, we have different, if an electron jump between different energy levels, we can know the difference of the energy of an atom. So delta E equals to, when you say delta, it's always final minus the initial. So plug in the numbers, that equals to negative 2.18 times 10 to the negative 18 joules, 1 over n final square minus 1 over n initial square. Okay, so that's the energy difference between 2 energy levels. And that difference of the energy can use to absorb or emit an electron. Sorry, emit a photon. So the energy to calculate photon, since we have one atom, so this delta E equals to h nu. We don't need to include n here. Okay, h nu equals to hc over lambda. Combine these two equations together, we can calculate the energy and frequency of emitted or absorbed light. Again, here, when you use this Bohr's model equation, the negative and positive in the delta E here on top only means whether there is energy needed or energy absorbed. When delta E is larger than 0, that means a photon is emitted. Okay, you have extra energy. When delta E is smaller than 0, then means you need to absorb a photon to compensate this energy difference. Okay, so besides these two equations of Bohr's model, we have another equation to directly apply to the energy difference of the two energy levels. So that's called Rydberg equation, that directly corresponding to the wavelengths of emitted or absorbed energy with two energy levels of a hydrogen atom. And this R is not a universal constant. It's the Rydberg constant. It's 1.079 times 10 to the 7th per meter. If used in equation, this constant will be provided. If used in exam, this constant will be provided. Okay, and for this N1 and N2, we need to make sure N2 is always larger than N1. If you say something electron is jumping from energy level 3 to 1, 3 is larger than 1, so N2 will be larger than 1. So what it means is to plug in N1 and N2, so the right item is positive. So you always have a positive wavelength. All right, so let's take a look at a question about hydrogen atom emission problems. An electron in the energy level equals to 4 of a hydrogen atom drops to a lower energy level. The atom emits a photon of wavelength 410 nanometer. A, what is the energy difference, delta E, for this transition in 1 mole of hydrogen atoms? B, to what energy level did the electron move? Here we give you the electromagnetic spectrum. Okay, so let's look at the question one by one. What's the energy difference of this transition and its hydrogen atom, right? So there are two ways of doing that. One way is the energy transition corresponding to the energy of emitted or absorbed photons. If we know the wavelength of the photon, then we can use this wavelength to calculate the energy of the photon, right? Wavelength to calculate frequency, then energy, okay, of the photon. Then we can get the delta E. Okay, and especially here it says 1 mole of hydrogen atoms. What we calculate from this wavelength is just 1 photon, right? So we need 1 mole of hydrogen will emit 1 mole of photons. So we need to use that times 1 mole, the Avogadro's number. Let's do this way first, right? So we can use the energy equation to calculate the light. Delta E equals to hc over lambda. Plug in all the numbers. Remember to convert the unit, every unit into meter. So 410 nanometer equals to 410 times 10 to the negative 9 meter. And then you don't need to worry about energy. Energy should be also in the basic SI, basic or derived SI unit. The energy unit for energy is in joule. Okay, plugging all the numbers, you get 4.8483 times 10 to the negative 19 joule. And for 1 mole of hydrogen, use that energy difference for 1 atom times the energy of Avogadro's number. And what you get is 2.9 times 10 to the 5th joule, 1 mole of hydrogen. Okay, so there's actually another way to think about that. Since it says emits a photon of wavelength at 410 nanometer, according to the electromagnetic spectrum, the 410 is in the visible light, right? So visible light is from 400 nanometers to 750 nanometers. 410 is right in this region. That means this hydrogen atom emits a visible light that immediately lets you know that it's the electron jumping from higher energy level to the energy level of 2, right? So if we know it's jumping between high energy level 4 here, to energy level 2, then we can use the Rydberg equation or the Bohr's model equation to calculate the energy difference between 4 and 2 energy levels, and then times that with 1 mole, the Avogadro's number. So we can do that this way. And then we can get a relatively similar answer. Well, there is an arrow here, right? So, and also this negative means emit a photon. It does not mean that, the energy is actually the energy difference is at negative value. This negative means it emits photon. And then it's only delta E1, right? So then you need to use NA, Avogadro's number, times this energy level. You can get a similar value here. So this question actually is not that accurate because you can see, compare the energy difference between the atom and the photon, there is actually quite a big discrepancy. So it's not accurate of this question, but ballpark, they are the same. Okay, it's in the same orders, and it has kind of similar values in the first part of scientific notation. And because of that, we can answer the second question quite easily. What energy level did the electron move? It moves to energy level of 2 because we have we have a visible light emitted. Or for question B, you can use this equation, plug the E1 you calculate from question A, and plug the initial as 4, you can calculate the final. And please make sure you round to the closest integers of this final, and then you will get the same value as energy level 2. All right, this is the end of this video, and I'll see you next time.